Yeah. Do you have a pointer or something? Hola, ¿cómo estás? But it doesn't matter. I can probably just point at the screen. So yeah, I think I'm ready to go. Is it mine? No. I just try to minimize the amount of. Hi everyone. So Andrew, ready to start? Ah, no, it's Andrew. I thought it was Andrew. Cool. So I'm very glad to be here to talk about crypto. So this is a bit of a last minute talk because I didn't intend to give a talk and there was, I think, someone dropping out. And then I thought, oh yeah, let's do a talk. I had some slides ready, so I could use those slides. So my name is Frank Zeyda. I'm involved with some of the communities here in Guadalajara. I've got my own embedded community. I'm going to say a bit more about that. Yeah. Yep. So I've worked both in academia and industry, and my interest is very mathematical. So I did my PhD in computer science, but I felt at the end it was more like a mathematics PhD. So I'm very interested in formal verification and rigorous engineering. So I don't just want to write code, but I want to know that the code that I'm writing is correct, or the design that I'm writing is correct. And in order to do this, we have a whole set of beautiful techniques and tools that we can use. And one of these tools I'm going to present here today. So I have previously worked at university, I've worked in industry, and right now I'm a freelancer, so I'm a consultant for a company in the US. Actually, two companies. One company is one of the it's called Galwa, and they do a lot of work in terms of safety critical, security critical engineering for governmental clients, for governmental research in the US. And I also work in another company which is interested in voting, verifiable end-to-end voting. Cool. So what's the objective? I want to explain you a little bit of the history behind Cryptol. So has anybody heard of Cryptol before? That's what I suspected. So as I said, this is not a language that you see every day. It's rather niche, but it's a very interesting language. And it's one which you can also very quickly learn if you have the right sort of mindset for it. So I will give you a brief introduction to Cryptol. And I want to explain a bit more the general picture, because Cryptol is a language, of course, that we can use for safe and secure cryptographic implementations and specifications. So it facilitates a lot of activities to validate our models, but it's kind of part of a bigger picture which we call rigorous digital engineering. So RDE has a few premises, which is that we want to use models, formal models, before we even write a single line of code. And we want to use these models not just because they're pretty and because somehow they will be forgotten on some slides, but we actually want to continuously use them for verification. So a lot of you probably use CI, CD stuff in Git, and we also adding CV to this, which is continuous verification. So whenever you're changing something, not just in your code, but also in your specifications, you want to be able to rerun all of that stuff to see, is my code still correct, consistent with respect to that. And I will say a bit more about applications beyond cryptography. So this talk is not going to be heavy on cryptography. I'm not a cryptographer. I work with cryptographers. I'm learning more and more about it. I find it super interesting. But I don't assume anyone else, especially from the community, to be sort of really into cryptography. So I try to give a more general picture. So what I mentioned before is that coding is actually not the main thing here. So when you engineer something in a rigorous manner, the coding should really fall out. Sometimes you don't even have to code because the code's generated for you. So my kind of suspicion is that a lot of times the coding is the thing that really you think is a productive thing in software engineering, and that's where the most of the effort is. But it's actually in this particular methodology, it's just something that is part of this life cycle. It's important, of course, but it's not the main thing. It's not where you spend most of your time if you do all of the previous stuff before. So formal verification is something which is a big subject. And this, I think, is a wordle from 10 years ago or something like that, across papers that talk about formal verification and formal methods. Formal methods always people get scared when they hear this term, formal methods. So we have to be very careful with language. But I could also call this mathematical approaches. And a lot of this is based on models, as I said. So we're writing models in different languages, like you write programs in Java, you write programs in Rust, you write stuff in Kotlin. We are also writing software engineering models of different kinds. They can be geared towards more general purposes. They can be geared towards protocols, security protocol verification. And Cryptol is also nothing else but a model. It's a model of some mathematical behavior. And then we're using logic to analyze these kind of models. And the difficulty comes when you have complex systems assembled of all these kind of different models. And how do you make sure that compositionally, when you verify something, the whole system still operates the way you want to? So there's a lot of terms here, some which is maybe more familiar, like testing, framework, and some things which may be a bit less familiar. Probably heard of Gödel in one way or another. Yeah, so this is just a quick overview, a bit scary maybe, but there's a tendency now which goes towards what we call secret ninja formal methods. So instead of actually having to do a lot of work yourself and employ 4 or 5 PhD students to do it for you if you're a company owner, we have no tools which can automate a lot of that stuff behind the scene. So if you write your specification, your program in a way that the tool can process it, you might have a really good chance to automate this kind of verification steps. And this is really where we're heading to and what the future of this should be. That we don't need to know but the mathematics and all the difficult, complicated stuff behind the scenes. But we can just use a tool, push a button, and getting some meaningful sort of feedback. So mathematics is a kind of superpower in this sort of engineering discipline. And this guy was really hardcore. So this is Evarista Galois. He didn't get very old because I think he was shot in a duel. And that was, I think, during the French Revolution. He was very politically active. Probably got shot in a duel over a girl. So I don't know, that was quite common in this time. And yeah, he developed a lot of mathematics that we're actually using, or the company's using as well. And you see Galois coming up everywhere. Even in cryptography, you have things like Galois fields. We have Galois connections, which are building kind of connections between semantic domains. And he solved also this problem that if you have a polynomial of degree 5, you cannot solve it generally. You know, when you have a polynomial of degree 2, there's a formula. And there's even a formula of higher degrees, like 3 and 4. Like they're a bit more complicated, but it's possible. But when it goes, sorry, I said 4. 5 is not possible anymore generally. And he gave a very interesting proof that bridges areas of mathematics. So this idea of bridging between areas is what I think is most interesting from a software engineering perspective, and also why the company I work for is called Galois, actually, in honor of Évariste Galois. So there's a disclaimer. So some of the remaining slides are not my property, and I gave the talk partly because I can save myself a little bit of time having to do all the slides. So every time you see this Galois logo, that's a slide that I sort of pinched from another deck. But I have the full permission to use all the slides, and I'm hereby attributing Galois as the owners of these slides, and they have the copyright. And also, I'm not representing Galois here officially. So everything I say during the talk is my own opinion, and in no ways should be associated with Galois or any other client. So just some formal stuff. So typical applications. So we have maybe some inline network encryptor. So we have an external network, and we have secret part of the network, and this device basically is purely implemented in hardware and to encrypt network traffic that arrives and passes it on. And this is a typical application in the DoD of cryptography, because they're very, very concerned that information which is under certain classification sort of restrictions is somehow exfiltrated. So they are very paranoid about this, and they need to have, devices, of course, like this in place. And this is a statement which is a little bit old now. So Daniel G. Wolf, he was the director of the Information Assurance Directorate of the NSA, I think a while ago. He isn't anymore, I think. But there's a few statements which I think may just explain a bit why we wanted to have a language for cryptography. So there's a lot of cryptographic devices in the US inventory, of which a lot of them will be replaced, because cryptography has moved a lot in the last 20 years. You cannot compare anymore the kind of cryptography we had at this point to what we have now. And the problem, there's a severe lack of diagnostic capabilities to evaluate these products for vulnerabilities and maliciously implanted functionality. And that's a really big problem, because this kind of evaluation is very intensive in terms of manpower, and it doesn't scale very well. I mean, depending on what you're giving to someone, it is very difficult for them to make a decision about, is this actually fulfilling the high standards that we need to have. So Cryptol started kind of I think in 1999. So John Launchbury actually founded the company Galwa, and was previously working at the Oregon Graduate Institute. And they already worked on something like a hardware, a programmable cryptographic chip that can perform different functions, and had a mathematically assured kernel on the chip. But they couldn't quite show that the implementation of these cryptographic algorithms was correct. But they thought that based on the research they've been doing, this was actually possible. So in order to do this work in a kind of proper and meaningful, not meaningful, but effective way, they founded Galwa as a company. And it was actually the first contract they had with the US government was to develop such a crypto-focused DSL, which later became Cryptol. And you can read more of the story behind it on the link below. So when they worked on this language in this contract, the motivation was that this goes a little bit back. So since the early 70s, so DAS was still kind of the officially approved symmetric key algorithm for cryptography, but it became clear that this was not anymore up to the security standards and too vulnerable. So they needed to have a new standard at this time. And there were a lot of proposals. So there were several designs proposed, and it's very difficult to compare these. So the Cryptol was basically a way the government wanted to analyze and understand these different proposals better. And this was one of the motivation. So it became a key part of NIST for their decision-making process. So they can use these cryptographic models in order to make more informed decisions. So nowadays, these algorithms are very well known. I mean, like AES is not something new, but at this time they were not that well known, and it was not so obvious what possible vulnerabilities these have, and understanding better the structure, the implementation of these things. So I think you need to see this in the context of the time as well. So if you assume you wanted to develop a DSL for cryptography, what are the constraints that you want to have in such a DSL? So one important thing of Cryptol is you want it to be executable. So you don't want just to have something which is a specification, but something that eases the way to implementation. And so that is one of the constraints that you want to put, and you want to be able to check your model in some ways. You want to run your model as if it was code, because we all like to code, and we all kind of using sometimes these kind of techniques to check if we're on the right path. The Cryptol specification should guide and document implementations. So a specification is useful if you can relate it later to an implementation. And there are formal ways of doing this, and I will say a bit more about this later. But what we really want to do is even to generate them. So once we've written the specification, that's it. Don't need to do any more. Don't need to sit down and write it in a language of choice. We can just generate it, because the model, as I said, is executable, and it's precise enough to do that. Also, it should be neutral to the platform. We don't want to bake in certain assumptions like von Neumann or Harvard architectures, partly because hardware is not constrained by these assumptions. So if anyone has done hardware design before, you really start from an empty sheet. You're making a circuit. You're not making a processor and memory architecture. You are really free in how you design your hardware. And the language, of course, should be high level. So, but this is a tricky one. So I talk a lot to cryptographer. And for them, a bit is something which is very high level. For me, it isn't. For me, a bit is something very low level. So there's always a kind of culture difference between formal methods and cryptographers. So what this means is really that it should be high level from a cryptographic perspective. So let's go to the next. So Cryptol, as I said, is a DSL for the specification, analysis, and implementation of cryptographic functions. It's very much inspired by Haskell. So you find a lot of similarities between Haskell and Cryptol. It has also some limitations. So it's not quite as expressive as Haskell, but I explain a bit later why that is. It's geared towards code generation. So it has certain idioms and paradigms that make code generation easier in Verilog and VHDL. There are other code, there's ongoing work on other languages which are targeted. But the initial motivation was basically these very hardware-centric languages. And it supports validation and verification of cryptographic models, both by way of testing, so some kind of automatic random testing, and mathematical proof. And this is really the interesting part, because you cannot always test everything. There's another slide later from Dijkstra, but if you really want to make sure that your algorithm is correct, testing might not give you that answer. So Cryptol, just to summarize how it differs from Haskell and other languages, it has rich data structures for cryptography. So in particular, you have, well, the common stuff like integers and floats. You have bit vectors, of course, that's very central to cryptography. You have ranges, which, I mean, some more modern languages like, I guess, like Scala have these kind of concepts as well. Modular arithmetics, and this is really important because a lot of cryptography is based, I thought I had another picture here, yeah, on this. So it's a clock. And the thing is, we all know these modular stuff because everyone programs and languages seen this operator, like, it's a percentage. But the mathematics behind it is very interesting because you're thinking about algebraic structures underneath these operators. For instance, when you have a prime modulus, then you can get groups out of your modulus, and these are groups with respect to addition and multiplication. So this is a very important part of cryptography. So this is baked into the language. Also, we have fixed and infinite size lists. Infinite because sometimes when you're processing data, you keep on processing, and you need to have an algorithm specified that never says I'm going to stop at some point. And of course, records and algebraic data types, which modern languages now have in a way. So records now are in Java since, I think, when Java was 15 or something, or 14, 17, yeah. And algebraic data types, in some ways, were always possible to do in languages like Scala, and I think Kotlin also supports that. In Java, it's a bit more difficult. I think they don't have it directly, but you can simulate it in some ways. So you can always encode this manually. We have a rich type system that enables statically enforced properties relevant to cryptography. For instance, if I want to say a number is prime, I can decide this on the level of type checking. I don't need to have a function like in checking that the number is prime. Well, I could have that as well, but I don't want to check this. I want to check this before I synthesize code. There's some idioms and constructs related to circuit design. I will say a bit more about this, but there's also restrictions. One of the problems is recursion. So when you synthesize into hardware, I mean, recursion is a very nice concept in high-level programming, and it maps very nicely to your architecture, but it doesn't map so nicely into a low-level hardware design. So some things are prohibited. So we don't have, unfortunately, recursive algebraic data types or recursive record types. So that's a main difference, or one of the main differences to functional languages. And also reference and pointers are forbidden. So everything is a value. And that is why functional programming is so cool and so easy to analyze, because we don't have pointers. So there are things like references even in functional languages, but you can either avoid them or stick to a language which doesn't include them, and which is pure in the sense that there's no side effects, like Haskell. So that is basically concessions that you have to make. And this is just an example, and I'm not sure how readable this is. So when you write a Cryptol function, you give it a name, and you give it a type. And the type can be parametric. So in Java, you also have generic types. So this K is a bit like a generic type parameter. But now you have a type which you have some operations, like must be greater than 2 and must be less than 4. So here's the thing. Numbers are types. So you have a type system, but every number is a type in its own right. And this is very much sort of inspired by the kind of dependent typing that you find in languages like Coq. I know, for instance, maybe not everyone heard of Coq. It's a very niche thing. But a lot of the proof system now go into a direction of dependent typing. So Microsoft's Lean uses the same paradigm. And it means that I can decide this at a type level. It's not a property of your language that the program will be rejected if this doesn't hold. It doesn't even compile. And this is a nice thing. You have this very strong type system. I could also say that K is prime number here. And these are the things that cryptographers sometimes care about, because when you look at some cryptographic algorithms, they have all these weird kind of restrictions. Must not be 2, must not be 3, must be a prime, must have, if you take, I think p-1 must have some large prime factors. Otherwise, the algorithm is unsafe. So there's all these little kind of constraints that you want to impose. Or in some cases, you want this to be a safe prime. So there's a special notion of safe prime, which is related to the concept, I think, of Sophie-Germain prime numbers. And you can all specify this within here. This is just a list type. So that means I have a list of 128 bits. There should be a bit afterwards, but if you omit it, it's just a bit. It's just a true or false. And you can also use the K value in this description. This already tells you that this language is a bit more expressive in terms of its type system than, the average JVM language or maybe C. So this is an example of a function, and I don't want to go in all the details of it, but just to throw it at you, basically, that you write for an encryption procedure. Now, this is a very weird way of writing things, I admit this, and it's a recursive value. So we all know recursive functions, but recursive values is maybe not so common because most modern programming languages don't support them yet. But you're defining a constant rounds here, which occurs within the right hand of the definition. And this is called a stream equation, because I'm referring back to the constant here, but I'm putting something at the beginning of the stream. And this is how you write stuff in Cryptol in this kind of slightly around the corner way to make the synthesis in hardware easier. Because hardware works really nice with these kind of equations. And there are means in Cryptol that you can translate this directly into a circuit that is clocked. And each clock cycle, it will generate you another element. And with this kind of descriptions, you make this kind of facilitates this kind of translation. So I don't want to go too deep what this actually means. This is a kind of sequence comprehension. So we're constructing some kind of list or sequence. In a programming language, you would say it's a list. Python has list comprehension. Java, I don't know. Probably not, no. Java doesn't have it. But I'm sure next Java version, maybe they will introduce, maybe even in Kotlin, who knows. So this is basically that we're quantifying over different values of different lists, and we do a kind of parallel composition, which is a little bit like a map function, but it's a kind of also a mixture of map and fold, because we're referring to the previous element back. So I don't want to go too much on about this, but this is how you would write code in a functional language that lends itself for the hardware synthesis. So I wanted to have a quick look at an example of this Enigma machine. And there's a tutorial in Cryptol that explains how this machine is encoded in Cryptol. I think there might not be so much time to do that, but I just will see if I can give you a quick idea. And the issue here is also that the font is a bit small, so it's maybe a bit difficult to see what goes on. But the Enigma machine is made of different components. And from a cryptographic perspective, it's not super difficult. It's basically a polyalphabetic substitution that takes place here. So you have a lot of permutations of letters. And the key thing is that the Enigma machine has rotors. And each rotor turns, and when one rotor hits a kind of a notch, it triggers the next rotor to turn. And there's a few other things that take place before you're sending the letters and after you're sending the letters. But you can encode this all very nicely in Cryptol. So we can define, first of all, a set of types here to capture the permutations. This is the initial permutation of this plug board, which always takes place at the beginning. So the rotors themselves can be modeled here. So again, you can define yourself a type for the rotor. And then you can have constructors for the elements of the rotors. And you can say, what is the permutation the rotor performs, and where's the notch that turns the next rotor. And if you ever programmed in a functional language, the nice thing about functional programming is extremely condensed. There's no noise. It's really just, this is what it is. And it is dense, but also there's no verbosity in it. So you can say, well, this is what the permutations look like. And this is where the notches are. So I can construct myself these objects, or these values. And as I said, Cryptol allows you then to specify, for instance, the scramble operation of a single rotor. And you're building a specification from these small parts. So in the same way you're building functions in an object-oriented language out of other functions, you're building it here from mathematical functions. So you define a function scramble, which takes some initial state and then gives you the output and gives you the new state. And from these then, you can use the language paradigms essentially to define these functions, what they actually mean, and compose them to end up with a full model of the machine. So we have, for instance, this join rotors, which takes a certain number of rotors. And what you can see here is that this is completely generic, because we could use any number of rotors. You can build your own kind of magical Enigma machine with, a million rotors if you want. So, and this allows you to build reusable parts of algorithms, cryptographic algorithms. And that makes this language also very useful because of its rich type systems. You can do that. And the specification itself is very, very condensed, very precise. And I don't want to go into all the details, and you can find this tutorial. But once you have once you've written this specification in full, you're putting all of these different parts together and define the state. Just have to find where I am here. Yeah, the state of this machine. So it's a very natural way to compose things. You have some record types where you have all the different components, you have all your functions in place. And right at the end then you can define what it means to encode something. And none of these functions is really big. Every function is just, a small piece of the algorithm. And you can verify each of these functions in separation. I can write tests for all these functions. I can do some write some mathematical models. So that's all possible to test these. Well, this is already a mathematical model, but I can write another model and see if it's equivalent to this one. So this is just a very quick introduction, and there's some examples here how you encrypt. And at the end, you have the tool, And when I load the specification, because the model is executable, I can just give it a sequence of characters and get the result and encrypt it. So let me just go back to the talk. And I need to play this again. Cool. So what are the benefits of using a language like this? So we want to have a clear and unambiguous model of the cryptographic algorithm. So everything is explicit, like bit order, endianness, and there's no kind of decisions that a programmer has to make which are not in the specification. How many of you might be asked to write a function for your boss or for your company? You have no bloody idea what that function should do. I mean, that is, I don't think that's very unusual sometimes. Sometimes you have to make up your own specification, but in this case, you're basically just writing the specification first, and then the implementer knows exactly what they have to do. And you can check that they've done it. That's the most important thing. So we want also have a language that is that experts of this cryptographic domain are familiar with. So a cryptographer can pick up this language equally than a functional programmer, for instance. As I said before, we can validate parts of the algorithm. For instance, I can run tests. I can run these functions. I can see what the result is. I can define properties, which I haven't shown you yet, but I can also say, well, if I encrypt something and decrypt it, is that going to give me the same text? And does it do that for every possible input? And that is something you can do with this language. Models are highly reusable because everything is just a function or a type. And when you write your model in a nice way, you have a good chance that you can reuse it. And specifications, of course, can be refactored. Again, owing to the fact that I have the explicitity of a functional language. So why do we want to implement these algorithms in FPGAs? So it's for commodity hardware, there's usually a lack of trust. So you cannot use kind of traditional software approaches. So I don't know what goes on inside a chip that I buy somewhere on Temu or wherever, I don't know. So and it's very difficult to evaluate if the system fulfills my constraint of safety and security. So hardware-only solutions are very common in a sense, because an FPGA is like a tabula rasa. It's something which can execute any circuit. And if you start to write a hardware design, you have to take account of every logic gate. So the language you're writing the stuff in will be translated into a network of logic gates. So there's no unknowns in there, and it's really interesting. I mean, if you have a bit of time and study a bit of hardware design, I did it outside university, actually, not even as part of my degree, and I found this super nice because finally I felt that I'm getting to the lowest level. Before I write some code and there's an operating system, there's a compiler, all the stuff in between. And if you program in the maybe 80s, you would write assembly code, so you're already lower to the hardware. But here you don't even have a processor, nothing. So you're really defining the circuit that runs underneath. So there are some custom crypto chips, but there's, again, this problem of standardization. They are often very complex. And FPGAs in some ways are more flexible. You can have a soft core which you integrate into a larger system, and if you know how it behaves, that gives you the kind of the same kind of assurance. And there's this kind of match between cryptography and FPGAs. So you manipulate arbitrary lengths of bit sequences in Cryptol, and this maps very nicely into these hardware description languages. And as I said, this parallel stream processing that I showed before also can be done very nice in hardware to give you efficient solutions. So Cryptol naturally in some way models hardware. So it is purely functional, which kind of corresponds to combinatorial calculations of networks of logical function blocks. You can map sequences to bit vectors. It is synchronous, so these stream equations that I showed can be very nicely mapped into kind of synchronous, stepwise clocked computations. And this declarative nature that you have also gives you more possibilities to parallelize when you generate the actual code. And the tools underneath does all of this for you, so you don't have to worry about how to do this. So when you have your model in Cryptol, this kind of gives you a bit of an idea what you can do with that model. So there's the Cryptol kind of processing stack, what happens with your model, and then you have on the right side the capabilities, what you can do as an engineer. For instance, once I have a Cryptol model, I have some simulation capabilities, so I can evaluate expressions, and I have model checking capabilities, which means I can check that functions are equivalent. And in functional programming, this is usually the paradigm of verification. Here's two functions, tell me if they're equivalent. It's not kind of trivial to do that, and I'll say this in another slide, but you can check, for instance, that your model that you've wrote, you have two functions that you wrote, that they are equivalent, but you can also later check that the model you synthesized is equivalent to the model that you initially defined in Cryptol. So you have this end-to-end verification in Cryptol that you can start from the highest level of abstraction, going all the way to the lowest level, which is just logic gates, and check that there's an equivalence between the two. This is how Cryptol compiles stuff, basically. So a high level of abstraction is this function here. And this function, as I said, uses this kind of particular way of writing stream equations. So you're taking a stream here, and you have basically picking, oh, sorry, sorry. You're picking basically an element from the sequence XS. In the next step, you're picking an element from the sequence where you drop the first element, and you're picking an element from the sequence where you drop the second element. So that gives you three elements, but they're different, they're adjacent in the sequence. So when this is a mathematically well-defined specification. But the problem is you cannot easily translate this into a hardware design. So assume you have a sequence which has this input 1, 2, 3, 4. Then what you get is basically always three values that you're adding together. And this is what the specification says. And you also see this inf here, which means you have an infinite stream. So the type system and the language supports infinite streams, which is important for, of course, for these functions, which never really stop. They just continue computing. Now, if I want to map this into a hardware design, what Cryptol does first, it uses this intermediate representation. So you have an input, and then you apply a function to this sequence where you're dropping one or two values, and you're adding them, and you're getting an output. But the problem is this is not synthesizable. So there's some more internal stuff going on where you're injecting delays. And once you introduce a latency, then this sequence, this operation here that you specify, that kind of looks ahead in time, becomes implementable. So the thing is, when you have these kind of recursive functions or value equations, you try to map them into something which is implementable in hardware. And you want to extract some kind of clocked circuit out of it. And in very short terms, this is what the Cryptol compiler does behind. So you have this signal, I think signal processing intermediate language. You're going to the next step where you're introducing things like these delays. And finally, you can go to some code. And this code looks like that. Now, it's probably hardly readable, and I don't want to explain really what it means. But this is how hardware engineers write circuits. Of course, they're not writing circuits like that, we have boxes, like you do it maybe in the university and school. They're using this higher level languages. But these operations here, for instance, are synchronous assignments. So you're creating some intermediate variables, you're making these synchronous assignments, and you're computing the output of this. So what you see, if you look at the details of this, is that there's some delays. So you're having some internal variables that just record the last value and the two values before. And the actual output that you are generating here is basically a mathematical operations on these things. So this shows you in a short terms how you can start from a very abstract mathematical formulation in terms of this recursive equation here, and you go down all the way to something which is extremely low level, because this is just synonymous for a circuit. So from this, you extracting a circuit as a bit stream, which you can directly run on an FPGA. That, this is not a very complex one, but imagine you have a complex cryptographic function that you want to execute. And the same principle applies. So the overall process of using Cryptol involves what we sometimes call stepwise refinement to implementation. You're starting from the most abstract, you're building a second model which is more concrete, but still mathematically precise. And this model then can be used for the generation of the code. And on the way, you're carrying out these kind of verification steps. So first of all, you want to know that your reference implementation and the target specification, reference specification and target specification are correct. So the high-level spec and the kind of more concrete spec, these two you want to prove to be equivalent. But last, you also want to prove that your netlist, which is just another fancy term for circuit, is also still correct with regards to your target specification. And the Cryptol uses these the Cryptol tool uses these thing called SAT and SMT solvers underneath to prove this for you. And the thing is, without verification, the only thing you can do is testing. And there's this famous quote from Dijkstra: you can always show there's bugs by testing, but you can't show there is no bugs. In most cases, at least, unless you test exhaustively. But the state space of these things are extremely large. You cannot often test exhaustively. And there has been a case study, which I might skip a bit because the time's getting a bit short, from Rockwell Collins, which use exactly this strategy. And they are doing design space exploration as well. So for instance, there are some, you cannot read this, but there are some design trade-offs of efficiency and space and time. And these you can also explore within the parameters of your model. And this what also makes this technique so powerful, because you want to have the model to be generic enough so that you can have the high-level correctness property, but at the same time you want to be able to change your parameters. You want to make changes, even swapping stuff in and out. I can have a function, exponentiation. How do you optimize exponentiation? Maybe you can exponentiate by, I think it's called squaring. So instead, you rewrite your expressions, and this can be implemented. So there's a lot of things you can do, which we do every day, but we don't care if it's correct. So in this case, you get actually a proof that if I have this piece of code that my sort of colleague wrote, and I think I can do it faster, then it's actually correct. So there's some lessons learned from this, is that these design space exploration can really generate some huge benefits. And you're also, saving time with this. So a Cryptol developer can do this maybe in a week, when an FPGA engineer might take months to do that, because they have to do this all at the level of the hardware. So the refinement, as I said, is integral to this approach. And I think even if you're not necessarily trying to optimize for speed, you still get, by this way of using idioms within the language, still very, very good sort of competitive designs in terms of efficiency. And that, that is actually quite nice when you do something mathematical, and at the end it's not just correct, it's also fast. And I didn't even, try to do it like that. But I mean, the tool just generates it for me. So as I said, this is something I've already shown in terms of the verification strategy. And it's just to show that all this equivalence checking can take place at different stages of the modeling. And I will skip this a bit. So this is just to tell basically that equivalence checking is not an easy problem. It's NP complete. We have some techniques to do it, but in general, you need some, sophisticated approaches to say, here's two circuits. How do you know these are equivalent? And there are some techniques that exist to do that, and all that stuff is a secret ninja in the background. So when I said the secret ninja formal methods, this is where it comes in essentially. And all you're getting basically is a result to say, well, they are equivalent or they're not equivalent. So there's a couple of algorithms to do that. Not going too much into the details. There's one thing I still want to mention. Now, if you don't want to generate code, if you, let's say, have some code already written, what are you going to do with that? Now, there's something called the Software Analysis Workbench, and this is also freely available, that supports various languages, not just Cryptol, but also LLVM, so therefore C and the JVM, and therefore Java and other JVM languages. And there's also some experimental work to support the MRI and Rust. And this allows you basically to mix and match. I can take a C implementation, I can a Cryptol specification, and then I can grind out some proofs that these are equivalent or that one refines the other. And they have actually done this for the HMAC implementation in Amazon's S2 and TLS library, but they have done it for many, many other things as well. So this is how you actually verify code. So rather than saying, well, I have my specification, I want to generate the code, now I'm taking something someone has written and try to verify it against the model that I've previously provided. And something that Cryptol also can do, you don't have to apply to cryptography. So there's an openly available repository of this Hardens project which provided an executable specification of a reactor trip system, which functions to shut down a nuclear reactor if, for instance, you have some measurements which are not inside their margins. And this is, of course, safety critical. And you don't want to, I mean, you don't want, if you have a specification of this and you have an implementation, you need to have very high guarantees that it actually does the thing that it should per the specification. There's other things that we can do. We can model codecs, CPU, state machines. So it's not restricted to Cryptol. But you're getting all the benefits. You're getting this functional equivalence checking. You get model versus code verification using the SAW toolkit that I explained, and the automatic code generation as well. So in conclusion, so we had a brief look at Cryptol, just to understand a bit more its capabilities. We studied the language a bit, see how it looks like, and explored this rigorous process and methodology of engineering systems and hardware, where we have these very high guarantees that our implementation does the thing it should. So I only briefly discussed this, but this is available if you're interested in that. You can also have a look at the documentation. And we looked at some non-cryptographic algorithms. And lastly, if you do love functional programming, Cryptol will be a breeze to learn. There's a few idioms, of course, which are not so common, but generally I think it's very easy to pick up. Some further reading. This is all available on GitHub. So both Cryptol and SAW are available on GitHub. And you can either Google it or you can just take the link. We also have resources. There's also some resources, including the tutorial I just showed you. So this tutorial here is actually the best point to start. So that is very deductive and enables you to learn more about this language. And there's a wealth of examples of predefined, pre-specified algorithms, which is in a separate repository, which is called Cryptol specs. And I'm not going to have a quick look now, but you will find there's a lot of cryptographic functions which already have been specified in there. So yeah, that's basically the end of the talk. I'm sorry I was overrunning a bit. And one last thing I wanted to mention is we have this hardware meetup group, ESG. And if you're interested, either take a picture of the link or just let me know, and we are meeting sort of once every 2 months, Hacker Garage usually. And we're not doing Cryptol there, so no worries, but we're doing some other nice stuff related to hardware. We're having talks like same way like the other meetup groups, sometimes more lower level hardware talks, sometimes more software related talks. So if you like to join, so you're welcome as well. So if you have any questions. Wednesday. Yeah? Yes, we do have a meeting this Wednesday. So just come along, you don't need to sign up. Wednesday, Hacker Garage in the evening, 7 p.m. So yeah. Cool. Do you have any kind of questions about? Yeah?
Well, hi. Thanks for the presentation. Regarding the intended audience of the tool, well, it seems to me that it is a tool for developers that try to port some kind of cryptography to specific hardware, or people or developers that try to design hardware, and not so much for cryptographers or application programmers in a general sense. Is that correct?
I would say not quite. I mean, the initial motivation, as I see it, was to target hardware. But likewise, you want to have a specification to really know what an algorithm is. So we're using something called literate specification sometimes when we're writing these models. So assume someone wrote, a mathematician gives you a sheet of paper and say, this is my new fancy algorithm. But we don't really know exactly what it means because he is imprecise. You're interleaving that with, formal definitions. So the Cryptol is really a formalization of that specification. So that's the first benefit. The second one is when you using the SAW tool, you don't have to target like Verilog or generate code in Verilog VHDL. You can likewise generate C code or Java code, and there's other work in progress. So it's not exclusively done for hardware. And I think the main benefit initially was, of course, to have a formal model, because there's nothing like that. It's just, reading papers. And I mean, who wants to read? Well, people want to read papers, of course, but software engineers usually, it's not always easy for myself to pick up the details of a paper that's been written by cryptographers. So I would say that the applications they're wider than just hardware. But of course, you're having these facilities in the language, and it's very much, it allows you to do this out of the box. And that makes it useful. I hope that answers the question.
Yeah, then the audience is like broad, yeah, yeah.
Yeah, I think there's definitely different applications. And as I said, this has been developed for 20 years, and it has gone into different directions. And not all of this is actually available, but there's different ways of using that, this approach.
Okay, thank you.
Cool. Yeah.
We have time for last question.
So I wanted to know, is there a software limitation in Cryptol for, let's say, like the amount of rounds that you can use like for a block cipher, or does it depend only entirely on the hardware that you're using in that moment?
I think from when you look at the verification, so I'm not super in the I don't know all the details of how the verification works, but I think from a verification perspective, if this encoding is done in the way I presume, that this would be this would not make a difference for the verification, because you're not you're using logical representations of these things. In terms of implementation, I think it's there's another process, of course. Once you have your VHDL, you need to give this to an EDA tool, and you have restrictions on your you have the technology mapping, you have restrictions on the resources. So I think this is not a restriction of the language, is a restriction of the target technology in some ways. So Cryptol itself doesn't have these restrictions. There may be some restrictions within the system when you do evaluation, for instance, when you have like this sort of interpretation-based mechanisms that there could be some limitations with that. I haven't explored all the details of that, but I think in terms of verification, in terms of code generation, I don't think there's fundamental restrictions. At least I haven't seen them. I mean, there could still be restrictions in terms of proof. If you have very complex models, but this is something you find everywhere. And sometimes you just need to have the right kind of lemmas. You need to give a little bit of help to the prover, figure out why the proof doesn't get through and things like that. So that's another problem. But this is a universal problem that you have when you do verification, because proof is hard. And it's just not easy to do it, and not by human, not by computer. Maybe AI will, change that in the future. I think, but it is that these are sometimes. But the proof tools are quite good sometimes, picking up patterns. And if you give the right kind of lemmas, then you can make it completely generic sometimes. Okay. Okay, thanks so much.